Hello everyone and welcome back to Thermodynamics. Today, this video will be going over a review of the topics that we'll cover on the second midterm exam. So if you remember, our first midterm exam was mostly about closed systems. How do we do conservation of energy in closed systems? Now, when I think about this second module where the material we're reviewing for this second exam, I think about this as being an exam on open systems, right? So how do we do conservation of mass and conservation of energy in open systems or control volumes? We've learned about how to do turbines, pumps, and heat exchangers, starting with this open version of the first law, making a series of assumptions and getting to some equation that will tell us normally either the power or the heat transfer rate as a function of specific enthalpies of the fluid that we're interested in. We've also talked about entropy and the second law of thermodynamics. We introduced the rate version of the second law that we would use for open systems. We talked about heat engines and refrigeration cycles, heat pumps as well. The difference between the heat pump and the refrigeration cycle is really just where you're standing, what the energy benefit is. Are you heating up the hot place or cooling down the cold place? We talked about the ideal version of those cycles, which we'll call a Carnot cycle. And then we defined parameters, characterization parameters for those different cycles. So for heat engines, we talk about thermal efficiency. For heat pumps and refrigerators, we talk about coefficient of performance. But we talked about both of those things as being essentially kind of fundamentally similar, where we're talking about what's the energy benefit divided by the energy cost. We also started to talk about isentropic efficiency so that we could calculate what's going on with real turbines and real pumps. And then we gave examples of how to chain different open systems together to make a heat engine. In particular, we did that with Rankine cycles. Now we know how to calculate Rankine cycles and to find the thermal efficiency, and then we compare that thermal efficiency of the Rankine cycle to the Carnot or maximum thermal efficiency. So what do you do if you're totally lost, right? You open up this second exam and you find that, oh no, I don't know what to do. So usually what I would say is we want to go through this process, right? As engineers, we like to have robust processes so that if we keep following a good process, we're more likely to get a good answer. So if you feel totally lost on an open system problem, the first thing you want to do is figure out what your control volume is. Where are the boundaries of your open system? Then you'll figure out what happens to the mass. So you have to do conservation of mass or continuity. Then you'll have to figure out what happens to the energy. Now you'll apply the first law. And then sometimes, particularly if you're designing a system, you might want to know, can this system operate in real life? Are you doing the equivalent of striking a match or unstriking a match? So are you generating entropy with your process? Conservation of mass looks like this, right? So we have the rate at which mass is being stored in our system is equal to the sum of all the mass going in minus the sum of all the mass going out. Common assumptions. Remember, common assumptions don't mean assumptions we'll make every time. They mean assumptions that you may make in specific cases. You might assume that this is at steady state, and then your energy or your mass storage term will go to zero. You might also assume that there's only one inlet and one outlet. And if you make those two assumptions, you'll find that the mass flow rate in is equal to the mass flow rate out. Then we have conservation of energy for an open system. Now, the first part here is basically the same as the rate equation for a closed system, where the rate at which energy is being stored in our system is equal to the heat transfer rate in minus the work rate or power out. But because this is an open system, we also have to worry about the amount of energy that's coming in with the mass and the amount of energy that's going out with the mass. So we have these extra terms that are related to the mass flow rates. dE by dt is the energy change, or the rate of energy stored in our control volume. Q dot is the heat transfer rate into the control volume. Remember, heat in is positive. The rate of work or power done by the control volume. So typically, if this power term or W dot term survives, it's because you have fan blades inside your control volume. Remember, hip to win, that means that work in is negative, which means work out, like you'd get from a turbine, is positive. This term is the rate of energy entering the control volume by mass transfer, and this term is the rate of energy exiting the control volume by mass transfer. Inside, we're tracking three different types of energy that can enter or exit with the mass flow rate. The first is the specific enthalpy, which we'll remember is really the specific internal energy plus the pressure times the specific volume. Then we have this kinetic energy term, V squared over 2. Remember, the units here are going to be tricky, so right now, this is the metric version of this equation because we're dividing by 2 and not 2GC. Remember, even here, we're going to have problems with units because typically this will give us an answer in joules per kilogram, whereas when we look up H, it's in kilojoules per kilogram. So we will often, but not always, divide this term by 1,000. The last term here is the potential energy term. Again, if this term sticks around, you've got to watch out for units because here you'll be getting joules per kilogram and not kilojoules per kilogram. Now, this equation becomes a little bit trickier if we're dealing with imperial units. So now these two terms, the potential energy and kinetic energy terms, they are the ones that get more difficult in imperial units. Because first, if we just take the velocity squared divided by 2, we don't get the right quantity. We don't get energy per unit mass. Same thing with the potential energy term. So what we have to do is divide by GC for all of these terms. That will give us the right quantity, but typically, if our velocities are in feet per second or our elevations are in feet, we'll typically get here foot-pounds per pound mass. But when we look up H in the textbook, we'll get BTU per pound mass. So not only will we have to divide by GC if we're dealing with imperial units, we'll also have to worry about unit conversions. So typically, if our velocities are in things like feet per second, we will also have to divide by 778 to turn those foot-pounds into BTU. But again, it's best not to just memorize that conversion, but to look at what your units are and use the right conversion factor. Because this will be different if we're dealing with miles per hour in terms of velocity instead of feet per second. But ultimately, when we're using the first law, anytime the kinetic and potential energy terms stick around, we have to think about the units, right? The hair on the back of our neck should stand up because we're starting to get into some territory where it's easy to make mistakes. Now, that's true when we're using the metric system, but it's doubly true when we're using the imperial unit system, right? So we always have to worry about units with these two quantities. Common assumptions, again, these are not assumptions we'll make every time, but common assumptions when we're using the first law, we might be at steady state. And in this class, this kind of introductory to thermodynamics, we're typically always at steady state when we're using the first law. One inlet, one outlet, so that would mean the summation signs would go away. The change in kinetic energy is approximately 0, so that this change in the kinetic energy term tends to be small. And we saw that in one of the examples that we did. We'll often assume the same thing for potential energy. And then often when we do these open systems, we'll think about simple systems where we either have power or we have heat transfer, but we don't have both. So often we'll cancel out one of these two terms. If we're in a cycle and we're moving between different open system components, we might also make some assumptions like no friction losses, so that our pressure from, let's say, an outlet of a turbine and the inlet of a condenser is the same. And we might also say that there's no heat loss in the lines, so that basically, again, that outlet state from the turbine is the same as the inlet state to the condenser. it's great. And I think that, again, if you don't know what to do, right, and you're doing one of these open systems, what you're going to do by employing or deploying these different equations is you'll get symbolic solutions. But inevitably in this class, you'll get to a point where you have an equation that looks maybe something like W dot is equal to M dot times delta H, or maybe Q dot is equal to M dot times delta H. So if you want a numerical answer, you'll have to figure out how to find specific enthalpy. Or ultimately, how are you going to fix the state? So ultimately, this comes down to a two-part question. So the first part is, what's the fluid? If the fluid is water, then you have to ask yourself, what's the phase? Is it subcooled liquid, superheated vapor, or is it some combination of saturated liquid and vapor? Is it under the vapor dome? Or you could have an ideal gas. And if you have an ideal gas, you'll have to ask yourself, can I assume constant specific heats, where delta H is Cp times delta T? Or is it going to be variable specific heat, where I have to use something like A22 if I'm dealing with air? So if I want to find delta H, maybe the most straightforward way to do this is if I have a two-phase mixture or a superheated vapor, then I can just look it up in the textbook. Or if I had an FE handbook handy, then I could look it up, but only if I had two-phase mixtures or superheated vapors. If I had a subcooled liquid, right, remember we can approximate H as HF at the same temperature, provided we're not going through an ideal pump. But typically, for subcooled liquids, if we had subcooled liquid at the inlet of a process and at the outlet of a process, maybe the cooling water in a heat exchanger, if this was at constant pressure, we would assume that delta H is equal to Cp, that's the specific heat at constant pressure, times delta T. So when we deal with ideal pumps, this is one that's it's easy for people to mess up. If you think about common errors on an exam, I think this ideal pump equation is one of those. So we forget that delta H for an ideal pump is the specific volume multiplied by the change in pressure. So this comes about from two things. So first, we have to remember that H is equal to U plus PV. And then second, we see from a second law analysis of an ideal pump that it's not unreasonable to assume that the temperature change across an ideal pump is zero. And if the temperature change is zero, we assume that delta U becomes zero. So then delta H in this case is really driven by this change in the pressure. Now here we take the specific volume times the pressure at 3 minus the specific volume times the pressure at state 4. Now the thing about water or most subcooled liquids is that they're incompressible, so that the specific volumes don't change very much as you change the pressure. So in this case, if you only know one of the specific volumes, that's okay. So often you'll have the inlet to a pump will be maybe some saturated liquid. So you'd have VF at whatever your inlet is. And you can just assume that both of those specific volumes are the same and multiply that by the pressure. Now, first, if people make a mistake here, maybe they just don't even remember that this is an equation that they can use. The other thing that people might mess up about this equation is the units. So it's really important because delta H, we want this in kilojoules per kilogram if we're talking about the metric system. And then we want to have our pressure in kilopascals, because if we take meters cubed per kilogram and multiply that by kilopascals or kilonewtons per meter squared, we'll get kilojoules per kilogram, which is what we want for delta H. You also have to be very aware of the units if you're using this equation in the imperial system. Now, if we're dealing with ideal gases, there's a couple different ways that we can find the change in enthalpy. So if we're assuming that the specific heat is constant, then we can say that delta H is equal to Cp times delta T. But remember, equations like that only work if we're assuming constant specific heat. If we can't make that assumption, or we don't feel comfortable making that assumption, we want to find how we get the individual enthalpies if we have variable specific heat. And in that case, we need to look at table A22 if our ideal gas is air, or at other tables in the textbook if our ideal gas is another gas that's not air. We've also seen that we can use isentropic efficiencies to find the outlet states for turbines and pumps. So in this case, we'd have enough information to fix the inlet state. Then we would find the isentropic outlet, typically by knowing something like either the temperature or the pressure, and then remembering that the isentropic outlet has the same specific entropy as the inlet. And then we would use the isentropic efficiency definition for either the turbine or the pump to find H out. So remember, when we have turbines and pumps, our isentropic efficiencies mean that the isentropic outlet is vertically down on this TS diagram for a turbine, vertically up on this TS diagram for a pump. But then the real states have larger specific entropies, so they both move to the right as they go through the real process. And we can use the definition for isentropic efficiency to find state 2 or state 4 if we know the isentropic efficiency. So what are our equations for isentropic efficiency? We have to remember that they're a little bit different for turbines and pumps, and that they always have to be less than 100%. So it's always going to be work over work, or power divided by power. One of these is going to be real, and one of them is going to be ideal. So we have to think about which one's bigger. So the ideal turbine, the turbine is producing power. So the second law, the irreversibilities in our system, rob us of the power that we're generating, because that power is a benefit. So in this case, the ideal turbine produces more power than the real turbine, right? So because turbines produce power, and that's a benefit, the second law, or the irreversibilities in the system, work to reduce the power in the real turbine. So here, our isentropic efficiency for the turbine is the real power divided by the ideal power. And we can get these equations from the first law. For a pump, the concept is the same, but the algebra is a little bit different. And that's because the pump consumes power, and that's a cost. So now, since pumps require power, and that's a cost, what the irreversibilities do is they increase the cost that we have to pay to run the pump. So in this case, the real pump requires more power than the ideal pump. So now we have the ideal pump divided by the real pump. And remember, our ideal pump power is going to be that specific volume multiplied by delta P, and we're going to have to mess around with the unit conversions until we get something that looks like kilojoules per kilogram in the metric system, or BTU per pound mass in the imperial system. We talked about Kelvin and Planck's statements of the second law. So Kelvin and Planck said that, yeah, we can make a system that's kind of running continuously where we input heat and we produce work. But we can't do this if these are the only two energy transactions that we're doing. We need to be able to cool down our heat engine so that it can run continuously in a cycle. So we need to also be rejecting heat from the engine to the cold reservoir. The consequence of this is that while we can take heat in and produce work, we can't turn all that heat into work because we have to have some heat rejection. Clausius told us that in the second law, we can make a machine where the cold side is colder than a cold place and the hot side is hotter than a hot place. So we can sort of trick the universe to make it look like we're transferring heat from a cold place to a hot place. But there's a price for doing that. So we can't trick the universe into transferring heat the wrong way and produce work. We can't even do this and have net work be zero. Instead, we can only do this by plugging this machine into a wall or some other way of adding power to the system. This is why your refrigerator doesn't run if you don't plug it into the wall, right? So we need to be able to transfer work into the system if we're going to make a machine that can remove heat from a cold place and reject heat to a hot place. We also talked about the second law in terms of a rate equation, and this is what that equation looks like in the elapsed time form as we sort of got to the rate equation. So here we know that the change in entropy is equal to the sum of all the heat transfers divided by the temperature of the surroundings, or the temperature on the boundary of our control volume, not the temperature inside our control volume. And then we have to add up all the entropy that comes in with the mass, subtract all the entropy that goes out to the mass with the mass, and then we have to look at this entropy generation term. And one thing that we know about every process that happens in the universe is that it generates entropy. So this entropy generation term always has to be positive. We took the same equation, we divided by delta T, and we took the limit of that equation as delta T went to 0. And now we get the rate at which entropy is stored in the system. This is not to be confused with the entropy generation rate. This is the equivalent of storing mass in my cup outside if it's raining. Then we add up all the places where heat is coming in or out using the same sign that we would get from the first law. We add all the entropy that's coming in with the mass, subtract all the entropy that's going out with the mass, and then we have this entropy generation term. And again, we know that the entropy generation term has to be positive. So this ds by dt term is the rate at which we're storing or depleting energy in the system. We have entropy that can come into or out of our system by heat transfer. Here we want to pick the temperature of the surroundings, the temperature outside our control volume, or sometimes on the border of our control volume. Because this is not a delta T term, we need to use absolute temperatures here. Then we can look at the rate at which entropy is entering our system by mass flow, the rate at which entropy is leaving our system by mass flow, and then we have this entropy generation term. We know that entropy generation has to be positive. If it's less than 0, then we know that that process can't happen in real life. Now, we can, here I said that it's in this, it says entropy generation term has to be greater than or equal to 0. But there's two cases here. So if it's greater than 0, that means that it's possible. We've satisfied the second law. If it's equal to 0, that's still impossible, but that's kind of the limit of the process that we can do. That's the ideal case, or the reversible case. Common assumptions when we're dealing with the second law is that we're at steady state, one inlet, one outlet, so those summation signs can go away. Adiabatic, so I won't always be able to make this assumption, but if I have the choice to make this assumption, I will typically make this assumption, because if I'm going to make a mistake, this is the term where it's easiest to make that mistake. So now, again, you can get a symbolic solution, and I'm always going to encourage you to find the symbolic solution first. I think this is kind of like that 80-20 principle, where you're doing 20% of the work, but getting 80% of the benefit by doing the symbolic solution. But when you get there, you're going to have to figure out how to find delta S. And there's different ways that we do that. So again, maybe it's easier if we're in the two-phase region or the superheated vapor region, because then we can just look it up, right? If we have an ideal turbine or an ideal pump, then delta S becomes 0 if it's at steady state, adiabatic, and one inlet and one outlet. So we sort of have to do a second law analysis to get to this point. But if we have an isentropic turbine or pump, we would consider that to be ideal, and the change in specific entropy would be 0. For a subcooled liquid, we're going to have delta S is equal to Cp times the natural log of T2 divided by T1. Two things about this. It looks a little bit, remember delta H was Cp times delta T? This looks a little bit like that, although now we have this natural log term instead of delta T. The other thing is that these are temperatures that stand alone. They're not changes in temperature. So we need to use Kelvin or Rankine when we're using that equation. If we're using ideal gases, we can get delta S from the tables. And if we get delta S from the table, we still can only get S superscript 0 from the table. So there's no table in the textbook that will just tell you what the specific entropy is for an ideal gas. Instead, table A22 for air will tell you S superscript 0. And that's basically what the entropy from the temperature is. So this delta S superscript 0 tells you what the change in entropy is because of the change in temperature. But you also have a change in pressure, which we model with this second term, which is minus R. Remember, R is the specific gas constant, which is R bar divided by capital M. And that's going to be R bar times the natural log of P2 over P1. Again, this should be absolute pressures because they're not pressure differences. So that's how we get delta S from the tables. If we don't have tables, if we're assuming this is constant specific heat, then we have to pick between one of these two equations. And we pick one of these two equations because we either know the temperatures and the pressures, or we know the temperatures and the specific volumes. So here, if I'm looking to do this, using the tables and using assumption from B are really the same thing, right? So if I want to get the most accurate answer I can, I'm really going to use this equation in part B, and I'll get S superscript 0 from the tables. And if I'm going to use constant specific heat, I use these equations, but I recognize that C and D introduce some extra uncertainty into my answer. So I'm stepping further and further away from reality as I make that specific heat, constant specific heat assumption. And that assumption gets worse the bigger my temperature difference is. So remember, S superscript 0, we looked this up on table A22 or A23. And that's only a function of the temperature. So when we find the temperature, we'll be able to find S superscript 0, but to find delta S, we have to add this R times the natural log of P2 over P1. So how do we find delta H for ideal pumps? So I already introduced this equation, but it's worthwhile to kind of go through how we got there, right? So now I'm finding my specific power. So this is W dot, big W dot divided by the mass flow rate. And we know that that's delta H, right? And if this is an ideal pump, this is going to be H1, that's the inlet to my pump, minus H2S, which is the isentropic outlet. Now I remember that H is equal to U plus PV. So H1 is U1 plus P1V1. H2 is U2 plus P2V2. But we're subtracting U2, so this becomes minus U2 minus P2V2. Since across this ideal pump, the temperature is constant. So T1 is equal to T2. So we're going to assume that U is only a function, so U1 can be approximated as the specific internal energy of the saturated liquid at that given temperature. And since temperature at 1 and temperature at 2 are the same, U1 is equal to U2. We can also approximate the specific volume that way, and we can say that V1 is equal to approximately V2. So the specific volumes don't change very much. So the change in the specific power across this pump, if it's an ideal pump, which is isentropic, is going to be driven only by that change in pressure. So here we would cancel out this delta U, and we'd pull the specific volume out. Now if we take that specific power and multiply by the mass flow rate through the pump, we would get m dot times P1V1 minus P2V2. But we've said that the specific volumes here are approximately constant, so we can pull that specific volume out, and we get that the power across this ideal or isentropic pump is going to be m dot times the specific volume times P1 minus P2. Now, because the purpose of the pump is to increase the pressure of the fluid, P2 will be bigger than P1, and we expect this pump power to be negative, because from hip to win, work in is negative. So how do I find the change in specific enthalpy when the change in specific entropy is 0 and I'm dealing with an ideal gas? So I have two options here. So if specific heat is constant, then remember we had this equation, these two different equations here, when we have delta S for an ideal gas with constant specific heat. If you rearrange these equations and delta S is equal to 0, then you can use these equations where you have a ratio of pressures is equal to a ratio of volumes to the power of K. Remember, K is Cp divided by Cv. That's 1.4 for air. Now, I can also have a ratio of temperatures to specific volumes to the power of k minus 1, right? So if I knew the temperature and the change in specific volume, then I would use this equation. In open systems, typically we'll know the temperatures and the pressures, and then we would use this equation, which also has k in the exponent. So this relates the ratio of temperatures to the ratio of pressures. And now my exponent is k minus 1 over k. So if we're dealing with an ideal gas and the process is isentropic and we've assumed constant specific heat, then we can use these expressions, which have k in the exponent, to find, maybe we don't know the outlet temperature of a compressor, but we know the inlet temperature, P2 and P1. Then we could find the outlet temperature of that compressor. So now, what do you do if you're dealing with an ideal gas that's an isentropic process with variable specific heats? So anytime you use variable specific heats, you can't use an equation that uses Cp, Cv, or K, which is Cp divided by Cv. So now we're going to have to use the tables. And the table that we're interested in, if we're dealing with air, is A22, and then A23, I believe, deals with other gases. And the properties we'll be interested in here are the reduced pressure and the reduced specific volume. So P subscript R and V subscript R. But how do we use them? So here, you'll go to your equation sheet and you'll look for the part that talks about isentropic ideal gas equations. So now, if I know the pressure ratio, which is often the case when I'm dealing with open systems, then I'll say that P1 divided by P2 is PR1 divided by PR2, right? So if I didn't know the outlet pressure of my turbine, P2, then I could use this to figure it out. Or if I had enough information to fix the inlet state of the turbine, so if I knew the temperature inlet of the turbine, I could find PR1. And then if I knew the pressure ratio across the turbine, then I could use this expression to find PR2. And when I knew PR2, maybe it's over here, then I can interpolate back and find the temperature. Or I can find the specific enthalpy. Notice also on this part of the equation sheet, you also have all those expressions with k in the exponent. So we've tried to take the equation sheet and group things together in places where it's useful to find them. So if you're dealing with an isentropic ideal gas process, you look at this part and you see, oh, am I going to be variable specific heat or constant specific heat, right? What do I know? Do I know the pressure ratio or do I know the volume ratio? So hopefully you find that helpful. And again, I'd always encourage you when you're doing problems to use the equation sheet so you're familiar with using it during the test. We also talked about system integration. This idea that we can take a whole bunch of components, right, like Lego blocks, put them together and make interesting thermodynamic cycles. In particular, we've talked about heat engines, right? So we talked a little bit about Rankine cycles, right? We made the allusion to things like heat pumps and refrigerators, talking about them from sort of a Kelvin and Planck or a Clausius perspective, but we'll eventually get into doing these component by component as well. Our general method for thermodynamic cycles is to first define the characterization parameter. So we're going to think about what's the energy benefit divided by what's the energy cost. Now, if it's a heat engine, we'll talk about thermal efficiency. If it's a refrigerator, then we'll talk about coefficient of performance beta. And if it's a heat pump, we'll talk about the coefficient of performance gamma. But if you don't want to remember which Greek letter goes with which, I remember beta goes with refrigerator because it looks a little bit like a capital R. But you can always just write COP for coefficient of performance. Then we'll look at all the different components and we'll do conservation of mass on all the elements. We'll do the first law on all the elements. And then we'll do the second law on all the elements if we need to demonstrate if something's possible. Then we'll be left with symbolic solutions where we'll need to know delta H or delta S. So we got to figure out what's the working fluid. And if the working fluid's water, then we ask what the phase is. And if the working fluid is an ideal gas, then we need to know, is it constant specific heat or variable specific heat. We use that information to fix all of our states and complete our state table. Once we've done that, we can find the power and the heat transfer for every component. And that'll help us figure out the actual efficiency if we're talking about a heat engine, or the actual coefficient of performance if we're talking about a refrigerator or a heat pump. If we want to, we can compare the efficiency of the actual or real cycle to the Carnot efficiency. Now we know that the Carnot efficiency or coefficient of performance has to be better because the ideal system will always do better than the real system. So how do I find the real characterization parameters? For thermal efficiency, this is going to be the desired energy effect divided by the energy cost. The energy effect for any heat engine is going to be net power, and the energy cost is going to be the heat in, not the net heat, but the heat that we're getting from burning coal. If it's a coefficient of performance, it's still energy benefit over energy cost. Coefficient of performance for a refrigerator, because we're standing on the cold side, we're interested in removing heat from the cold space, so it's going to be the heat transfer rate on the cold side divided by the cost, which is the net power. For the heat pump, it's similar, but the energy benefit is the heat transfer to the hot place. And again, the cost is still net power. Both of those coefficient of performance should be absolute values. So if you get a negative answer because your Q dot term is the opposite sign of your W dot term, just take the absolute value. The Carnot characterization parameters come from these same parameters. So the Carnot thermal efficiency, we have W dot net divided by Q dot in. But if we did a first law analysis of the closed system, that's our whole Rankine cycle, that's going to be Q dot in minus Q dot out. And then we can divide that by Q dot in to get our thermal efficiency. Now, anytime we have a ratio of Q dots, we can get the ratio of temperatures to be the same thing if we're going to be an ideal case. So I can substitute this ratio of heat transfers here for a ratio of temperatures if I'm talking about the ideal or Carnot efficiency. So here, my 1 minus Q out divided by Q in is 1 minus T cold divided by T hot. Because where I'm rejecting heat, I'm doing that to my cold reservoir, and where I'm adding heat from my hot reservoir. If I'm looking for the Carnot coefficient of performance for a refrigerator, I again start with the real coefficient of performance for a refrigerator, but when I get to this ratio of Q dots, I can turn that to a ratio of temperatures. I can do the same thing with the Carnot coefficient of performance for a heat pump, remembering that the difference between the heat pump and the refrigerator is the energy benefit. So in the energy benefit of the refrigerator, we're removing heat from the cold place, but the energy benefit from the heat pump is that we're adding heat to the hot place. So here I have T cold, and here I have T hot. Remember, whenever I'm using these equations, I always want to use absolute temperatures because some of these terms are not delta T's. So that's sort of general heat engines, heat pumps, and refrigerators. But then we started to work on our first cycle. And this is the Rankine cycle that gets used in nuclear power plants and coal-fired power plants. We can draw a TS diagram here. So the whole purpose of this Rankine cycle is to go back and forth across the vapor dome. So if you're drawing a TS diagram for a Rankine cycle, you have to draw a vapor dome. Remember, what we're trying to do is produce power in this turbine, and then the rest of the cycle is just to get back to the turbine inlet. So we're trying to produce power from the turbine, and then we cool down the steam that comes out of the turbine so that we have a liquid. We use a pump to increase the pressure of that liquid, and then we use the boiler or steam generator to get steam and boil that high pressure liquid. Then we can go back into the turbine. So my actual thermal efficiency is going to be the net power divided by the heat in. My ideal performance, or my Carnot engine performance, is going to be 1 minus T cold over T hot, using absolute temperatures. We also define this characterization parameter called the backwork ratio, which recognizes that the first consumer of power from the power plant is the power plant. So we want to see how much pump power is used relative to the turbine power. So this says basically what percentage of the turbine power goes back to power the pump so I can run my system in a cycle. When I'm trying to analyze one of these Rankine cycles, I look at each component. I do conservation of mass, although for this sort of basic 4-component Rankine cycle, it's all steady state, all one inlet and one outlet. So there's only one mass flow rate for the whole problem. Common assumptions for the first law include steady state, one inlet, one outlet, neglecting changes in kinetic and potential energies. And then depending on the component I'm talking about, I'll say the component is adiabatic for the turbines and pumps, or passive for the heat transfers. So when I'm rejecting heat or when I'm adding heat in the boiler. I'm also going to assume that there's no friction losses, so that there's constant pressure when I'm adding heat or removing heat, or if I'm moving between components, and that there's no heat losses either. So the only place that we are transferring heat out of our system is the condenser. When I do this, I get some expressions that are familiar to me. So if I can make all those assumptions, then my turbine power and my pump power are m dot times h in minus h out, and the heat transfer in the condenser and the boiler are q dot equals m dot times h out minus h in. I expect my turbine power to be positive because I'm producing power. My condenser, I'm rejecting heat, so that's heat out. That should be negative. My pump is adding power into the system, so this should be negative. Work in is negative. And I'm adding heat at the boiler, so this should be positive. Now I've got symbolic solutions, and I've got to say, what's the fluid? When I'm talking about a Rankine cycle, the fluid is water or something like it, where I'm going back and forth across the vapor dome. And I have to ask myself, how do I find delta H in all these different cases? And I think the one here that's the trickiest one is the pump, particularly when we're talking about that ideal pump, where delta H is the specific volume times delta P. And that concludes our review for the second exam. Good luck, everyone.